are down, power lines are down.
Message of 290 characters follows.
Hello everyone, and welcome to another episode of Grid Down Comms Up. Today, we're going to talk about near vertical incidence skywave and why, as someone in the preparedness community, the emergency communications realm, you need to understand this topic because this is critical to your ability to communicate when all else fails. We spend a lot of time in the preparedness community talking about VHF and UHF, talking about handheld radios and things like that, but we are not spending enough time talking about the way you really communicate when nothing else works. And this is with HF radio and near vertical incidence skywave. And why is this important? Well, one of the reasons it's important is it's capable of overcoming physical obstacles. If there's a mountain range in your way, it does not matter. If you are sitting at the bottom of a valley between 2,000-foot tall mountains, it does not matter. You can still communicate. So the ability to overcome geographical terrain that is causing a physical line of sight problem with VHF and UHF is one of the big reasons why we need near vertical incidence skywave. It also allows us to communicate beyond line of sight, where the curvature of the Earth actually starts to impede our ability to communicate with traditional line of sight radio. And for two people standing up, that actually happens to be, a 6-foot tall individual holding a radio around 5 miles. I know a lot of you guys probably have seen that on the bubble pack radios at Walmart. You can reach 5 miles, 2 miles, whatever. That's based off of two people holding them with nothing in between on flat land in the plains. That's about how far you can see before the curvature of the Earth starts to get in the way. Well, it doesn't matter with near vertical incidence skywave. Not an issue. NVIS also does not require a lot of power when used correctly. A lot of us use something called QRP or 10 watts or less in the ham radio world to communicate with near vertical incidence skywave and data modes. In fact, I've done a lot of communicating below 1 watt with near vertical incidence skywave and data modes. So this allows us to communicate efficiently in an environment where replenishing power is not always easy. It requires fairly minimal equipment. There's no need for repeaters. There's no need for other infrastructure. It's your radio and an antenna. If you can communicate with voice, that's all you need. If you're going to communicate with data modes, obviously you need a computer or a tablet or something that's low power consumption that you can use with it. And if you're going to kick it old school, then a straight key or a paddle where you can run Morse code and you can communicate no problem with minimal power across a mountain range through whatever terrain using near vertical incidence skywave. As I mentioned before, it doesn't require repeaters. It doesn't require infrastructure in order to communicate over a distance. It is a radio and a wire, and that's it on both ends. NVIS can also be difficult to radio direction find. Now, this is something we could do an entire long discussion on. So we're going to take the really high 30,000 foot approach of this, where if we terrain mask, so we hide behind a mountain, we use very low power transmissions, we can get ourselves into a situation where the signal almost looks as though it's coming from everywhere, and it's very hard to get a fix on where it is coming from because, one, it is so weak, and two, we don't have a good line of sight or way to get a bearing on it because the radio waves are radiating at an angle that makes that difficult. And we'll get them more into how that propagation works in a minute, but it can be difficult to radio direction find, giving us a level of protection that we don't have when we're using radios that are line of sight. Additionally, we are picking bands that reflect off the atmosphere instead of passing through the atmosphere into space, making it more difficult to radio direction find in that way as well. So, here are some myths of NVIS, and I didn't get them all. There's lots of them. If you spend some time on the internet, you listen to people on the internet that don't really understand NVIS or near vertical incidence skywave, you're going to hear all kinds of incorrect information. One, it takes a special antenna. No, it doesn't. You can use any kind of horizontal antenna that has a high angle of radiation, which is generally caused by putting the antenna to a low level, not high up, and we're going to talk in detail about that in a minute. But it doesn't take a special antenna. A dipole will work just fine. An in-fed half wave works fairly well. An off-center fed dipole. Most antennas can be configured in a way that works with NVIS very well. It doesn't take special magical skills. There are some folks that look at NVIS and are like, that's magic. I can't make it work. I don't know how to make this work. This is something that's just totally outside of my wheelhouse and realm. It's not true. It's actually fairly simple. The concepts are not that hard to grasp. You can get really into the math and how it works, and we're going to do a little bit of that. But it's not. It's just principles in physics, and it's all very easily explainable. NVIS does not work during solar minimums. Well, that is not true. I have operated plenty of NVIS during the solar minimum we had a few years ago. It works just fine. The catch is the frequencies that work for NVIS sometimes go much lower at night during a solar minimum, requiring us to use frequencies for NVIS that maybe we wouldn't ordinarily use, like 160 meters. There were times a few years ago where if you wanted to operate NVIS after about 9 p.m., 10 p.m. at night, you needed to use 160 meters because 80 meters was too high in frequency. So again, this is something where you have to understand some of this propagation, and we're going to get into that in a minute about really how that works. The next is that NVIS only works on one band. That's not true either. I've heard people say, oh, well, you have to operate on 80 meters to do NVIS. You have to operate. Nope. Any band that will reflect directly back down at Earth when you radiate RF at almost 90 degrees straight up from the surface will work. And that band changes throughout the day. In the afternoon, in the peak of the afternoon, it might be close to 10 megahertz. Most of the time, it's around somewhere above 7 megahertz. At night, it may drop, well, it will drop down towards 3 megahertz, so we're in the 80 meters range. In between, 160 might be the best choice. And as I said, during grand solar minimum, sometimes you had to go all the way to 160 in the middle of the night to get NVIS to work. And I realize that's hard for some people, but that's the nature of NVIS as we look a little deeper into that. So how does NVIS work? So we've got this lovely little chart here that I borrowed off the internet. I can't really find anybody originally to attribute it to, so if this is yours, sorry. But it is a great little sketch that I've seen in a lot of different books, and it shows the different layers of the atmosphere. And you can see we start here at the bottom with Earth, and we go up to the troposphere at about 15 kilometers, and then we have the stratosphere, the D layer, E layer, the F1, the F2 layer. Those are the ones we're going to talk mostly about, is the F1 and F2 layers, or at night they collapse into a single F layer. And with NVIS, what we're doing is we're radiating RF with the intent of skipping it off of that F layer, using the F layer to reflect it back to us, just like a mirror reflects light, so that we can communicate directly around us with that signal that reflects back. Now, during the day, when it's expanded into all these different layers, we have to pick a frequency that will pass through the D layer, reflect off the F layers, and then come back to Earth with enough energy to be received. Now, at times during the day, lower frequencies, 80 meters, 160 meters, that doesn't work as well because the D layer absorbs a lot of that energy, and we have to use a lot more power to try to punch through that, where we might be better served to move to a higher frequency that will just slip right through and then reflect back off the F layer. So that's something to consider. And if you've listened to shortwave radio or that kind of thing throughout the years, will understand that those stations change frequencies throughout the day in order to use propagation to get to the target audience they want to reach. So those that are operating in that 6, 7, 8, 9 megahertz range of the day are targeting people within a fairly close circle around them, about 400 or 500 miles. They use higher frequencies to go much further. And then at night, those 6, 7, 8 megahertz frequencies go much farther because they have less loss as they're passing through the D layer. So, why do radiation angles matter? Now, this is where we're going to get into the nuts and bolts of how near vertical incidence skywave works. So here we have in the bottom left of this kind of graphic, we've got our transmitter. And this gives us a really good illustration of about how far we can expect with what radiation angle our antenna is radiating RF at. So if we want to be, we assume for this, we're making some assumptions. We're assuming that the F layer height is an average of 250 kilometers above the surface of the Earth. So for those of you guys that didn't like trigonometry in high school, a lot of this is defined by trigonometry. And if you want to actually figure it out and do the numbers, you can do the trig and figure it out. I'll show you a little equation here in a little while to help a little with that. But there's some rules of thumb that we can apply. So if we look at this graphic here, the transmitter's in the bottom left at 85 degrees of radiation angle. So 5 degrees off perfectly vertical. Our RF is coming back down about 28 miles away. So if we're trying to communicate in that very close to us circle with rugged geography around us, like say you're like me and you're in the Smoky Mountains and you need to communicate 10 or 12 miles over some very rugged terrain to someone you don't have line of sight to, well, your radiation angle is going to be close to 90 degrees. So if you're using an antenna that doesn't put much RF straight up, it's going to be much harder than if you pick an antenna that puts the RF where you need it. And then we see here, at 65 degrees, we can communicate out to 150 miles. At a 50 degree radiation angle, our RF is going about 270 miles. So you can see, even if you're in a very tight valley, getting a 50 degree angle from where you're at to get 270 miles away, very doable. The mountains become an issue when you're wanting to radiate RF at 20 degrees or 25 degrees to try to skip across the ocean and get, a country in Europe or that kind of thing. But for our purposes of near vertical incidence skywave of NVIS, where we're focusing on that 400 miles, maybe 300 miles and less around us, or even that 15 miles across town through the mountains, this is what we're looking at and where we're focusing. And it's this higher angle of radiation that matters. So, kind of look at this, think about that, go outside with your protractor if you need to, look at those angles and just get an idea. This is pretty straight up. calculating radiation angle, and this is using a flat Earth approximation. No, I'm not a flat earther. We've talked about the curvature of the Earth already, but we are going to cheat some here to make the math not really terrible. So our angle, which is theta, represented by theta, is the arctangent of the vertical height divided by the range, or horizontal range, divided by 2. So if you use this equation, you can figure out the radiation angle you need to communicate between 2 points. And I use an example. If you use 160 miles or 250 kilometers for the vertical height, that's the distance it is up to the F2 layer, or the F layer. Then you put your horizontal range in the same units, obviously. If you're using miles, use miles. If you're using kilometers, use kilometers in there, and then solve the 200 or 160 miles over 28 divided by 2 arctan, you get an angle of 85 degrees. So if you want to do the math, that's how you can do the math. I just thought I'd throw that in there if somebody wants to geek out and play with the equations. Why does radiation angle matter? Well, we've talked about how it matters in reaching the distance we want to communicate. We've talked about how that at 28 miles, we're looking at like an 85 degree angle of radiation. Well, now let's look at antennas and why the radiation angle of the antenna matters when we look at this. And these two graphics here really illustrate this. And again, I borrowed these from Google. If they're yours, thank you very much for creating them. And I'll be happy to attribute them to you if I know who you are. But I've seen these in several books and some other places I've looked, so they seem to be fairly common. So let's talk about the dipole up here and kind of look at this. So we have these numbers right here that show us a distance above ground in wavelengths. And this is important because our blue circle is 0.1 wavelengths above ground. So it is very close to the ground. And we see that we have a very, like almost a squished circle a little bit. And we have some loss. It's not super efficient compared to a half wave, which is this red, very oblong, almost looks like a donut type shape here that is a half wavelength. Generally, we consider a half wavelength height on a dipole to be somewhat of an optimal distance above the ground for a horizontal one in order for the pattern of the dipole to fully form. Higher is obviously better, but generally the baseline is a half wavelength up. But we realize if we look at this, and like here at the very top in the center, we see 0 dB. That is assuming that we have 0 dB of loss, because all these numbers are loss or efficiency, below a dipole at a half wave. So we're using that as our reference as the dipole, a half wavelength in height. So if your dipole, or if the frequency in question is 40 meters, then 20 meters high, or about 67 feet, would be a half wavelength in height. Now, most people who are listening here don't have an antenna that's 67 feet high. So this is kind of illustrates the point that this is not exceptionally difficult to accomplish to get NVIS. So if we look at 0.1 dB here, this blue circle that's kind of squished, we realize that we're maybe 4 dB down from a dipole. That's not bad. It's, a little more than half your power is not being radiated, but it's still radiating more in the direction that we want it to go than a half wave dipole would be. We're at 90 degrees. It's 12 plus dB down. It looks like, in the graphic here. And you can model this stuff with the numerical electrical code and reproduce these. But the thing we want to take from looking at this here is if we look at the we look at the pink circle and the blue circle. So that's 0.25 and 0.1 wavelengths above the surface of the Earth. So at 0.25, we are maybe 3 dB down from the maximum lobes at you have a half wave dipole, half wave above the ground. So that's very good for what we want to do with NVIS. Optimally, usually about a quarter wavelength high is where we want to be. But we're not going to stay on one band. We're going to operate NVIS on multiple bands. Now, if you're only, like you're setting up portable, you're just going to work, you got some more flexibility built in to configure it for the band you want. But if we're bouncing between 40 meters and 80 meters, well, that 0.25 wavelength ends up being, very close to that 0.1 wavelength on 80 meters. That's like, I'm not going to do math here in my head, but for you guys, because I'll end up making an error. But it works out that 0.25 wavelengths, or about 30 to 33 feet up, really is a good place to put your antenna. It doesn't have to be super high. If you get your antenna 33 feet off the ground, 30 feet off the ground, you get really good NVIS propagation on 40 meters, about as good as you could possibly get just with a simple antenna. And you get on 80 meters about 3 dB worse, which is a half S unit. So it works really well on 40 and 80 for NVIS. So when you're targeting to set up an NVIS antenna, that 33 foot height is the sweet spot we want to aim for to get good NVIS propagation. Now, it's also important to look here that if we go to 0.3 wavelengths, which is almost laying on the ground, okay, we're still only 10 dB down from, or we're still not quite 10 dB. We're 10 dB down, but we're not quite that 12 and a half, 13 dB down that we would be seeing from a half wave height dipole. And I realize that's not optimal. It's far from optimal. But what I want you to see with that is, if you're in a situation where you have to run a compromised antenna and you can only put it like head height, 6 feet off the ground, it's still going to work better than a dipole that's a quarter or a half wavelength above ground. Not much, but it'll work slightly better. So when you're doing field portable stuff, when you're doing field ops and you can't get your antenna 35 feet up in the air, don't be afraid to lay it in the top of a hedgerow and make that NVIS contact, because it will work in a pinch. So now, if we look down here in the bottom right corner, we're going to talk about a problem that a lot of people don't understand. Maybe it's not, I don't know how to explain this, but we're going to talk about this issue. And this in the bottom right corner is the radiation pattern of a couple of different types of vertical antennas. Not a horizontal wire, but a vertical. And we have a quarter wave ground plane, a 5/8 wave antenna, and a vertical dipole, which is a half wave antenna. And if we look at these, we will see that most of them really don't have very much radiation. They have on the order of minus 30 dB of radiation from their main lobes, from the maximum pattern. This isn't reference to a horizontal dipole, but this is reference to the max radiation that they could have, where most of their energy is. They're 30 dB down in the center. This is significant. This is why verticals don't work for NVIS. And there's people out there that will say that verticals do work for NVIS. Well, they do work for NVIS in that the 30 dB down from your main carrier is going up at the angle that you need it to be. So, for example, I have over here in the corner some math worked out. So if you're radiating 100 watts, put 100 watts into your antenna, at 90 degrees straight up here, you got the same effective power that you would have of 0.1 watts. So all your power is going towards the horizon where you don't need it for NVIS, and you're only putting a very teeny amount straight up. If you happen to be an angle out where you're getting into these kind of upper funny lobes here where the 5/8 wave and quarter wave labels are, you may be getting 10 watts of that 100 watts effective in that direction. So, yeah, you can do it. You can also use a chain link fence as an antenna. Doesn't mean it's going to be a good antenna. And this, kind of goes to show that it doesn't take much power to make RF or to make NVIS work, because there are people who will cram 100 watts into a vertical and they'll still make NVIS contacts because a tenth of a watt's really all they need. So, if they hung up a horizontal antenna, they would have much better performance at a much lower power. So these are things to consider, because a lot of people, they'll be trying to run a vertical. Verticals, just they're great if you want to do. You see the low angle of radiation here down in the, this line here that kind of sticks up, and subdivides the 90 degrees 45. So, you subdivide that again through here, you get 25. So your main lobes are below 25 degrees. You're putting that RF towards the horizon to get a long way. If you want to communicate across the country or across the ocean and you can't get an antenna a half wave up in the air, a vertical's not a bad choice, especially on the higher bands, the 20 meters, 15 meters, that kind of thing. But for the mission that we have of NVIS, a wire laying in a hedgerow is probably going to outperform a vertical 10 out of 10 times. It's just the way it is. Now, all verticals, and there's lots of things that impact this with the conductivity of the ground, what's around it. There are a lot of things that can impact your real world performance. This is modeled stuff, but it does tend to work. I've made a lot of contacts over 200, 300, 400 miles with 1 watt or less with a horizontal antenna, a dipole particularly. I like dipoles, and with minimal power and no problems. You typically can't do that with a vertical. Now I want to talk about end-fed half waves. We all love them. Some of us love to hate them. There are a number of compromises that occur with end-fed half wave antennas. And let's always remember that an end-fed half wave is a half wave antenna, same thing as a dipole. A dipole is a center-fed half wave. An end-fed half wave is a half wave that's fed from the end instead of the center. So one of the benefits of an end-fed half wave is they are multi-band. They work on harmonics where dipoles don't. So people like them because it's an easy one-wire multi-band antenna. But we want to talk about here where that, when these diagrams, we're going to talk about how that can kind of mess a little bit with our NVIS performance if we're not careful, particularly with 40 and 80. And that's really what I want to talk about here. So if we look in the top left here, we have this diagram that has lambda over 2, which is a half wavelength. It looks much like a dipole radiation pattern. It radiates directly off the sides, kind of in a donut. Then if we move to the left, or not the left, but if we move to the right, you'll see that we have a full wavelength. So this would represent an 80-meter wire being used on 40 meters, where it's a full wavelength on 40 long. We start to develop this null in the center. Now, these antennas are modeled a half wavelength up. When they're low to the ground for NVIS, this is not really what the patterns are going to look like exactly. There's a lot of things that are going to mess with that. But the point I want to get to here is with NVIS, your antenna pattern and its upward radiation with an end-fed half wave, when you start getting, like here in the top right corner, a full wavelength, or if we look down here in the bottom left corner, 3 half wavelengths, so a wavelength and a half, our pattern starts to look really weird. That's something to consider when we're using an NFET half wave, is it may not be as perfect as we would expect with a dipole. And sometimes we get some strange things that happen there. With NVIS, it's less of an issue than it is when we get them up a half wavelength and the patterns fully start to form. As you can see here at like 3.5 wavelengths, if you go read some of the old military manuals on multi-wavelength directional antennas, there's tricks that they'll do with loads, like resistors, where they'll basically suppress 1/2 of that pattern to give them directivity in one direction off the end of the wire. Not something we're going to go into here, but there's some cool stuff like that has been done throughout history using these, but realize that those things actually can be used for benefit, but we need to understand they're happening when we're setting up an NFET half wave, because sometimes we get unexpected results that we should be expecting, but we don't understand what's actually going on around that wire. So, I like with my NFET half wave, I do like I would do with a linked dipole. If you don't know what a linked dipole is typically used for field portable, where we make a dipole, center-fed dipole antenna. And at the bands we want to operate, we cut the wire and we put a link where we can connect and disconnect it. So we can have it tuned to 10 meters, and then we can plug more wire in and get to 20 meters, and we can plug more wire in and get to 30 meters, and so forth and so forth. You can do the same thing with an NFET half wave. I typically cut mine at 40 meters because I use that of the day, and I don't want to deal with that extra 66 or so feet of wire. And then I roll that out, and then if I need 80 meters, I can couple the extra length onto it. And then that way I'm always working with a half wavelength, where I want to work. Something to consider, something to think about when we're looking at how our antennas react with NFET half waves. Another thing I want to point out to us here, and this was, I borrowed this from VU2NSB's website. He's got some really cool models done on antenna radiation, and this one doesn't have 80 meters. I wish he had one on 80 meters. But these two are on 20 and 40. And the reason I included this is I want to talk about the inverted V. If you're not familiar with an inverted V, it's where that we take a dipole, or you can do it with an NFET half wave, and you support the center of the antenna, and then the wires come down at an angle, looking like a V that's turned upside down, or a Christmas tree. And the thing I want you guys to notice about this is, in the field, we want quick setup, quick tear down antennas. And putting both ends of a dipole up in a tree can be a bit time consuming at times. But tossing one rope in a tree, hoisting up the center, and then just stringing out the legs in a V pattern is a much quicker way to set up an antenna. And if we look over here on the right at the inverted V versus the dipole at 35 feet, we were talking about that quarter wave up, and we look at the elevation pattern and the azimuth pattern here, they're not horribly different. The dipole is actually maybe squished even a bit more. The difference is very small between these. So again, this is something to not sweat. If you need a fast setup NVIS antenna, use an inverted V. I love inverted Vs. They're a great solution in the field because you just suspend the center, stretch the wires out, and go. Very, very easy because you just really need that center vertical support. And then you can just stretch them out at an angle with some extra rope to keep the ends up off the ground and tie them to a rock or whatever. Doesn't require a lot of trees and a lot of supports the way a dipole does. And you're supporting your coax with the support in the center, so you can get away with much smaller wires than you might normally use if you need to be worried about having to support the weight of your coax. So inverted Vs work pretty well for NVIS. I ran one for a couple of years and had pretty great results out of it. So when we talk about NVIS, we need to understand how the bands change throughout the day and how propagation with the atmosphere and different frequencies affects our ability to use NVIS. So this is from a website called that the Australian government runs that calculates the maximum NVIS frequency, or the maximum FOF2. And I've gotten some screen captures here of several different times of day UTC. So if we look here in the top left corner, you'll see that this is at 0200 UTC. So for most of us in the northern hemisphere in the United States, this is somewhere in the 9 p.m. to midnight range, depending on which time zone that you're in. And if we look over here, and of course this was done in September, if we look over here and we look at our colors in this left side, we can see that a good portion, well, almost all of the U.S. here has a maximum NVIS frequency of between 6 and 7 megahertz. So we're starting to lose that effectiveness on 40 meters for NVIS at this time of night. The sun has set. We're moving into nighttime propagation at this time, and we're starting to lose 40 meters or 7 megahertz as an option. It still works here in a few weeks. As the sun sets earlier, it's probably not going to work at 0200 anymore. But this shows us, it changes depending on where you're at in the world, what time of day it is. If we move over here to the right and we look, we'll see that, in the middle of the night at 0930 UTC, the most of the U.S. Is in the 4 or 5 megahertz NVIS realm. So we would be in the 80 meter or 60 meter area. Most of us would just go to 80 meters at that time of night for NVIS. And then if we look down here in the center, we're at 1715 UTC, or kind of in the middle of the afternoon for a lot of us, early to middle afternoon. We'll see that across the U.S., our NVIS frequency is it's getting up there in the 10 megahertz range. So 30 meters might be an option. And this window is fairly small when 30 meters is useful for NVIS. Usually we're still better off on 40 meters, but there is in the very center of the day sometimes a need to jump up to 30. But typically 40 works fine for these shorter NVIS. If you're trying to get out on the edges of NVIS where it's, you're maybe 250, 400 miles out, and 30 might be a better option. Which, remember, 30 is a digital and only band portion. There's not any voice there. So if you're constrained to voice, then that's not an option. But this is something to understand, that throughout the days, throughout the seasons, so each time of year, the times at which these changes happen vary. That's one of the reasons it's important to operate and important to do this and practice and train this and learn a little bit what to expect as the seasons change. The same is also true of the solar cycle. Right now we're closer to a solar maximum than a minimum. The bands behave very different now than they will during a solar minimum. So when we're dealing with NVIS, we need to understand all that. And I know this sounds very complex, but if we look and we boil all this stuff down, if you don't take anything else from this, realize that 30 feet up in the air, 40 meters and 80 meters. If it's dark outside, use 80. If it's daylight outside, use 40. And that's going to cover your NVIS needs out to a couple of 100 miles. Just those simple rules of thumb. 30 feet in the air, 7 megahertz of the day, 3.5 megahertz at night. And probably 90% of the time, that will do what you need it to do. So what sort of expected range? So I picked Waynesville, North Carolina, particularly the Folkmoot Center, where Heritage Life Skills, if any of you guys ever went to the Heritage Life Skills event put on by Carolina Readiness Supply years ago when it was indoors, I'm using that location as a reference because I'm fairly familiar with that area. And it's in some very rugged terrain, so it gives us a good example of this kind of stuff. So we're going to use Haywood County, North Carolina, as our example. Also, with Hurricane Helene, year ago, a little more at this point, this is a good example of some of the stuff that we had to deal with and do to communicate during that emergency, and would have become even more critical had the Mount Mitchell repeater stopped working, but we're not going to go down that path right now. I could talk about that a lot, but this is a 28-mile circle as the crow flies around Haywood County, North Carolina, Waynesville, particularly, the Folkmoot Center. So this gives us an idea of that 5 degrees off 90, that 85-degree radiation angle, what we would be expected to communicate with using NVIS. So that would get us from Waynesville over to Asheville, almost get us north to Hot Springs, North Carolina, almost gets us south to the South Carolina line, gets us back to the west just past Bryson City, and covers a big portion of the Great Smoky Mountains National Park. So that's an example of a 28-mile radius that we would expect to get with that high angle of radiation. This is a 150-mile circle around the exact same location. You can see this takes us almost to Lexington, Kentucky, takes us all the way down to Augusta and Atlanta, and gets us all the way to Charlotte and halfway to Nashville, Tennessee. So this is a fairly large circle in this area that covers, that 150-mile radius that is very easy NVIS communication. And at the kind of outer edge of what we would consider NVIS propagation, we have a 300-mile radius. 300 miles takes us all the way to Evansville, Indiana, almost to Columbus, Ohio, south of Savannah, Georgia, includes, Birmingham, Alabama, and all the way into West Tennessee. This is a big circle that we can communicate with, kind of on the outer edge of what would be considered near vertical incidence skywave. So this gives us an idea of what we're capable of with NVIS. And this is important that we understand that, because in an emergency, in a regional disaster, this is a very large chunk of area. This is a huge area of operations and a huge area that we can communicate in and communicate very dependably in. This is not a random happenstance. Is the band going to let us talk here? No, this is very dependable every day, all day. You can do this with NVIS, barring some solar storm that blacks out communications and that kind of thing. Now, there's another interesting application online called VOACAP, or was designed by the Voice of America, or VOA, and this helps us chart propagation and the percentage and likelihood of making a contact in different areas based off of, we give 2 points, we give our antenna parameters. So to give you guys a little information here, the antennas here that I selected when I picked the model for this were dipoles in that 0.1 to 0.25 wavelength height for 80 meters and 40 meters. And we've talked about that 30-foot height. And this is with 28 miles. So I picked across the Great Smoky Mountains National Park here. Again, we're using the Waynesville, North Carolina location we used before. And I used across the Smoky Mountains because that really kind of pushes home the point of geography doesn't matter. The terrain doesn't matter. We're going from a valley where Waynesville is down into the edge of Pigeon Forge, Tennessee, where the Smoky Mountains are in the center. And if we look over here on the left at our propagation wheel, and we look at the 0 at the top, we see the different frequencies or bands going down: 10, 12, 15, 17, 20, 30, 40, 60, and 80. And it's colored to match our percentage of likelihood of contact. And if we look in the circle all the way around the perimeter of the circle, this is the time in UTC or Zulu. So if we look at 0, that's midnight UTC, or depending on whether you're daylight savings time or not daylight savings time here in the eastern part of the United States, that's 7, 8 o'clock at night, I believe. So if we look here, we'll see that around midnight Zulu, that 40 meters, our propagation percentage is going from 100%, and it's decreasing as 80 meters starts coming up closer to 100%. And pretty much all the way through here until 40 meters starts picking up, except for one little time spot in the wee hours of the morning, around 6 a.m. or so Eastern. We have a close to 100% chance. We're in the 90s the whole way and don't ever really drop into the 80s. Now, and then at the daytime on 40, we're solid, when that falls off. I want to point you guys over here to the right side and the details of what I picked for this model. You'll note that I'm using CW. So most digital modes that we use will decode when you can't even pick up Morse code. When it's hard to copy Morse code by ear, Contestia, definitely JS8 call, even MFSK will still decode fairly well through, with a signal that is even at times hard to copy CW. And I used only 1 watt of power. So that's the important thing to also note on this. Guys, I'm using virtually no power here. And I'm communicating 28 miles across the Smoky Mountains with Morse code or easily any digital mode that we wanted to use. And the odds of this happening are of a successful contactor in the 90 plus percentile all day on 40 or 80 meters on the day that I calculated this. Like I said, obviously solar blackouts and sunspots and things like that can temporarily disrupt this, but this is just a good approximation of what we can expect. We're going to look a little bit further out. If we stretch this out to 150 miles, same parameters, 1 watt, Morse code, 35 feet above the ground for the antennas on both ends, and we look at 150 miles. So we'll take the same spot in Waynesville, North Carolina, and go to Chattanooga, just south of Chattanooga, just a little bit. And again, we're going to see that 40 meters may work a little bit better for a little longer here because we're a little further out. And then 80 meters picks up, but we're in the 90 plus percent success rate at 1 watt with Morse code for this distance. And we're going to look even a little further out here. We go to Evansville, Indiana, and we look at 300 miles. You can see that, again, 40 meters is getting a little more effective, a little longer, because we're at a little bit lower angle. We're getting down closer to 80 degrees. So 40 is going to work a little bit longer, and then 80 picks up. And throughout here, through the day, we're at pretty much 100% chance with 1 watt Morse code. And then overnight, our percentage goes definitely down into the 90s and maybe into the upper 80s for success rate on 80 meters. It might take a little bit more than 1 watt to make this work, but with digital modes, I would expect this to still work just fine. Now, let's talk a little bit about history, because NVIS is not new. We've been using NVIS, even if we didn't call it NVIS, for a very long time. And let's talk about World War II here. So a quick historical example. It is about 150 miles from Normandy to England. I have a typo in my slideshow there, if you guys notice. I'll have to fix that. But from Normandy to England, it's about 150 miles. And in World War II, one role of radio and NVIS was to communicate across the English Channel back to England. We also used radio to communicate from England back to stateside. Obviously, that wasn't NVIS, but still, we used HF radio to do all of these things. And typically, over this distance, they would have been using Morse code. Many of them would have never dreamed that they could have carried a RTTY machine in their pocket in the form of a cell phone they could hook to their radio, or in the form of a very small laptop 100 years later that they could use to send RTTY instead of Morse code. Because if that had been an option, I'm sure that would have been undertaken. Now, they were using RTTY in World War II, but they were very large mechanical radio teletype machines that were relegated to ships and fixed installations, because those things, if you've ever seen one, are not exactly something that's backpack portable. So we think about that and how much further ahead we are today, and how we can leverage tools that back then people would have only dreamed of today very easily. If we look here at a prop wheel, that 150 miles across the English Channel, 1 watt CW, very comparable to what might have been possible with a little tube radio back then. Honestly, they would have been using more power than 1 watt, probably more along the lines of 5 to 10 watts. With Morse code, it's an easy contact. It's, obviously in a combat zone, everything is harder. But as far as radio propagation goes, it's very doable. So this was something that was very doable. I want to take just a second here and go down a rabbit trail that's not related to NVIS at all, but something I want to explain to you guys. If you look over here at the left on the prop wheel that shows all this stuff, and we look at 12 and 15 meters here that have a 10% chance in blue. It's worth noting that 10% chance in blue on 15 or 12 meters is not NVIS, obviously. That is long skip. That would mean that rather than skipping from France across the channel to England, we are actually skipping south across Europe, across Africa, and around the South Pole back to England. We have a 10% chance of doing that. Not a very good chance of doing that, but understand that's where that's coming from on the higher bands. Is there is a long path propagation possibility there, though it's a pretty far out, unlikely one. Again, I just wanted to make sure you guys understood what that was. So we see here, historical examples of where that radio communications were an example, of that kind of thing. So let's temper some expectations here on this, because we've talked about all this amazing stuff we can do with NVIS. The charts and the numbers and everything make it look like this is a cakewalk and this is going to be easy. And I can throw this out and talk 28 miles away or RTTY or whatever, 28 miles away to my friends that I need to communicate with. And there's a very high probability that this is going to be exactly true. But if it doesn't work, there are some things that we need to understand. So noise floor. This is just the ambient noise around your receiver. If you live in a place that you have S9 plus noise, I feel sorry for you, and you probably need to go find and get rid of whatever it is. In some places, that's very hard to do, but understand that noise has a lot to do with your ability to receive. And if you have noise that's masking those signals, especially when we talk about like 1 watt, half watt, when we're dealing with weak signals to begin with, we have noise floor issues. And a lot of people that have trouble receiving, oftentimes they have a noise floor issue. It's if you've not experienced it, this is one of the beautiful things about operating portable. NVIS is easy to do portable, again, because you don't need a high antenna. I can take my 20-foot long fiberglass mast that I can throw in my backpack that weighs like 12 ounces and get an antenna 20 feet up in the air on 40 meters of the day in the field in a couple minutes, and it works great. But the thing to note is that gives you an opportunity to go places that have low noise floors. If you go into the middle of the Smoky Mountains National Park, throw an antenna up somewhere and try this, you're going to find that your noise floor may be an S2, maybe an S3, maybe even an S1. And you're going to hear signals that you don't hear at home, weak signals, because the noise floor at home is so much higher in your suburban or urban environment. So understand that noise floor can really impact this, and this is something we have to fight and we have to work around. You also need to understand what your antenna is really radiating after line and antenna efficiency, what the effective radiated power of your antenna is. If you're using a non-resonant antenna and you're using an antenna tuner to tune it at your radio, you're burning off a massive amount of power in your coax and in the inefficiencies of the antenna. And it's possible that, only a tenth or less of the power that you're putting out of your radio is actually getting coupled to the ether and, going and doing radio propagation things. The rest of it's being used to warm up your shack. So when we start talking about low power things, again, I like dipoles. In-fed half waves are okay. But understand, in-fed half wave may be 70 to 80% efficient. So you're losing 20, 30% of your power in that matching network potentially. But so understand that when we're dealing with minimal power, we need to make sure we're actually radiating that power. And we need to be careful of not using, I know some guys like to use random wire antennas. I'm not much of a fan of that because they tend to be less efficient. Another thing to consider and pay careful attention to is solar cycle and seasonal changes. So understand that all this stuff is going to be different throughout the seasons in the solar cycle. We talked about this earlier. If what was working 3 months ago is not working now, then take the parameters we've given, that 10 megahertz and below, the 30, 40, 60, 80, maybe even 160 frequencies. Use the information we've talked about here and try something different. Maybe at 9 o'clock for all summer and the time you've been practicing, 40 meters was solid. You took a couple weeks off for fall break and you come back and now you can't communicate with your friends anymore on 40. Probably ought to jump to 80. Understand. And then understand as the solar cycle goes through as well that there's going to be variation in that. And that's one of those things where the communications requires some experience. Last is field practice. You got to get out there and practice setting up a field portable station. You can set up your home station, tweak it to perfection. In a disaster, in emergency communications, you're probably not going to be using your home station. You're probably going to be using a field station. You're probably going to be set up somewhere that's not exactly the perfect location. And you need to understand your gear and how it performs, what its gotchas are, what its unique things are that you may have to deal with and work with in order to make your setup work, and understand how your setup works and what's normal function of your setup and when something is wrong. And if you don't do this frequently, you don't do it in different times of the year, you don't do it at the daytime, you don't do it at the nighttime, you don't test all these things, then you're going to have issues when you're faced with that situation potentially. In training a lot, we will say, you don't train until you get it right. Train until you can't get it wrong. And that is an important thing to consider here if communications for you is not just a hobby. It's not just something we do to have fun and blow off steam on Friday night after work or go set up in a park to have fun. It's something that we practice because someday we might need it to save our lives or the lives of others that we care about. It requires a higher level of training. And fortunately, amateur radio gives us a vector in which we can train and do that that otherwise we wouldn't have. So learn that stuff, temper those expectations just a little bit. You'll be amazed at what you can do once you start practicing. But understand you're going to have bumps and hiccups along the way, and you're not just going to get the stuff out of the box and it's going to work beautifully. Sometimes the bands surprise us. Sometimes we get exceptional propagation that we are not expecting. So this was done with my field station. This was a field portable radio running 1 watt at around 0200 Zulu. Little couple hours after sunset on a simple dipole 30 feet up in the air. And that magic number we were talking about for NVIS. In this case, I was operating on 40 meters at night, so I wasn't really just NVIS anymore. But I was running JS8 call, which offers some wonderful weak signal capabilities at a hefty price of speed. It is an extraordinarily slow way to communicate. In fact, plenty of Morse code operators can outrun JS8 call very easily. But it does provide some great weak signal capabilities. And I was able to, with 1 watt, get signal reports from all over the U.S., Canada, and some reports in Europe and Africa with 1 watt. So understand that sometimes during great propagation, it doesn't take much power to get a very long way. And that's the thing we have to learn with the atmosphere. It's also important to realize, a lot of operators will think that their station, especially if you're new, you got maybe a questionable antenna, and you're messing with JS8 call because JS8 call is kind of easy for a lot of people to start with. It also masks a lot of problems. You get stations that go, oh, hey, I've got 6 or 8 people who are hearing me on JS8 call. My station's working. This is good. Well, maybe it is. Maybe it isn't, because JS8 call doesn't need much to cover a big area. And if you're punching 100 watts or 50 watts or even 30 watts out of your radio on JS8, and you're only getting a couple of stations that hear you, you probably have an antenna problem. So just things to think about and things to understand. There are lots of tools like JS8 call and PSK reporter, Whisper, other things we can use to test our stations. But it's also important to have some friends that you can really get out there and use, VAR-AC or WinLink or FL-Digi, things where you can send much higher rates of speed, 32 plus words a minute, where if you needed to actually move some real information with digital modes, you would be able to do so, not banging it out at 8 or 10 words a minute. Keep that in mind. Understand that you can do a lot with a little power, but you also have to pay attention to the details, because a lot of power can cover a multitude of issues at times. So that is our conversation on NVIS. I hope that this helped you guys to get a little bit better grasp of kind of how near vertical incidence skywave works. It's not as complicated or magical as some people think. I went into a lot of the math, a lot of the tech behind it, a lot of the complexities behind it. And you don't have to memorize, you don't have to learn all of that, but it is beneficial to have a little bit of a foundation for how this works, so your expectations of how it works match a little more of reality. So I encourage you guys, get out there, toss an antenna up in the air, 20, 30 feet, whatever. Usually, you can throw a rope in the air 20 feet pretty easily. Get something up in the air and get on the air, try it, get some practice with it, maybe grab a couple of friends in your area, and you do that kind of thing. I haven't bought one yet. I'm looking at the True SDX, little 5 watt QRP radios, like $150 on Amazon. It's a very cheap entryway into HF, and I'm going to be doing some testing on one of those hopefully soon. As an option for folks that want to get into this, particularly, they're not interested in communicating across the country. They're just interested in communicating across the county or a couple counties away, as a very inexpensive way to get into this. So more to that to come, but get out there and practice. This is a valuable skill, and it's something that is falling by the wayside in a lot of ways. Satellite communications have eliminated a lot of the need for HF communications and HF propagation knowledge and that kind of thing. The adventation of automatic link establishment, ALE, in the military has kind of pushed aside a lot of these skill sets. But there could be a day coming soon where this is valuable knowledge and this is a valuable skill set. So take some time now, learn it, and have fun with it too, because it can be fun as well. That said, I hope you guys enjoyed this, and we will catch you next time on Grid Down Comms Up.